Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be looking at ionic equations. So this is a way to look at precipitation reactions, because precipitation reactions, due to the nature of having aqueous dissolved species, means that there's multiple ways we can look at these reactions. So we're going to be looking at three major methods: molecular, complete ionic, and net ionic. And each one of these is going to convey slightly different information about the reaction. So last time we built up a molecular equation. So this is where we treat all of our species as full compounds, even when they're in solution. But remember, potassium iodide will dissolve. Lead nitrate will dissolve. And so even though we tend to use, these will be the actual solutions, we'll take off the shelf, dissolve in water and mix in order to make lead iodide, which again, this is a method you can use to look for the presence of lead in solution. But that kind of begs the thing, is that it doesn't require the lead to be present as lead nitrate. It might be present as something else. And as a result, this doesn't quite depict all of the possible uses of this particular precipitation reaction. However, this method is really useful when trying to figure out how to mix up a set of chemicals, or when trying to perform stoichiometry, because since I take potassium iodide off the shelf, that means if I'm trying to figure out how much lead iodide I can make, I want to start with the mass of that species. However, it doesn't really indicate what's happening in solution, because I really am not going to have potassium iodide dissolved in solution, nor am I really going to see lead nitrate anywhere in the water. Because when I throw them in water, one of the things that first happens is they separate out. So potassium iodide isn't potassium iodide. It's potassium, comma, iodide. The two species are completely wandering through water, completely separate. Remember, they're both surrounded by a huge sphere of water molecules that cause these two to not really see each other in solution. And that is perfectly fine. But it leads to this kind of misnomer when we look at the molecular equation, that thinking that these two complexes have to interact. However, one of the things you should make note of is that if I have anything that is a solid, like my lead iodide precipitate, or any liquids or gases, these tend not to dissociate, and as such should be treated as molecular species. So the lead iodide won't separate out. So if I'm going to perform a complete ionic equation, what I do is anytime I see an aqueous species, I write it as its constituent ions. So instead of 2 potassium iodides, I write 2 potassiums plus 2 iodides. And then the lead nitrate is similar, 1 lead plus 2 nitrates, because we have 2 nitrates and lead nitrate. On the right-hand side, the potassium nitrate is dissolved, so 2 potassiums, 2 nitrates. But the lead iodide is a solid, which means it doesn't participate in the solution because it's a precipitate. And so this is actually a pretty good way of depicting how the system actually forms in solution, what's actually going on. I have a whole bunch of these random ions moving around, and 2 of them occasionally bump heads and form a solid. That's a complete ionic equation, and it really depicts what's actually present. However, you may note that this takes a little bit long to write. Notice I had to put it over 2 lines. And chemists, being the lazy people we are, want to have a neater way of depicting this. So you'll notice that a lot of these ions occur both in reactants and products. So I don't really need to include them on both sides. So I'm just going to cancel out any of these so-called spectator ions. These are simply going to be any ions that are freely dissolved in solution and don't end up changing identity, whether it's oxidation state or charge. They don't dimerize. They literally are in the same phase and form on both sides of the reaction. So if I have any of these spectator ions, I just cancel them out. They're a product, they're a reactant, they don't add anything. So we eliminate these and we form a net ionic equation. So in our net ionic equation, lead only shows up on the left-hand side, and again, on the right-hand side, it's part of the lead iodide. Same thing with the iodide. And so In general, when we're making these net ionic equations, the easiest way to start is by first writing out your full complete ionic equation, and then mixing anything that's present on both sides. And this is going to generally produce this nice streamlined form of the ionic equation. However, it is worth noting that this is often a lot more useful because when I do have a precipitate reaction, the spectator ions really don't matter as long as they don't form a solid. So the reaction of interest really is present in this ionic equation. So it includes all of the necessary information. So when you're trying to figure out the right equation to use, think about what you actually want to know. If you plan on doing stoichiometry or mixing things together off a shelf, go with the full molecular equation. If you really want to know what's present in solution because you want to make sure that you don't have any side reactions and you want to know what might just be hanging around, go with the complete ionic equation. It's sometimes important to know we have free potassium hanging around. However, if you really just want to focus in on what ions form your solid, go with the net ionic equation. It contains all of the necessary information. So with these three in hand, we have a good way of looking at our precipitation reactions. So next time, we're going to move on and take a little bit more close look at acid-base reactions and dive in and get basic. Until then, take care.